All right, good morning, chemists. Let's get started. Is this microphone working? Is it working? Yes? Yes? Yes. Okay. We'll get started now. I just wanted to do a quick announcement about the LRC, the tutoring center that chemistry has to offer. As a reminder that this is a free option available to everybody. The LRC is now open in business hours, so I think it's like 9 to 5, maybe 8 to 5, Monday through Friday. But the new thing this year that you might not be aware of is there is 2 locations for chemistry help. The first floor in the back of Celeste, the same building you have your labs, that's more for like lecture material, midterm preparations. Thank you. Midterm preparations, and then there's another tutor space in the second floor of Celeste, and that's more for lab related materials. So it's perfect. It's right next to your lab space. So both of those spaces, NETA will be able to help. And as a reminder, you do not have to go to your TA. We have a fleet of like 200 teaching assistants helping us run the chemistry department. And all of them are chemistry experts and will be able to help you. We all teach the same thing. So you do not have to go to your TA unless you really like them, but any TA should be able to help you, all right? And so there's the information there, but just know the locations. They're open during business hours. Okay, so plan is to finish up chapter 13 and start chapter 14. So if you have grabbed those chapter 14 slides, and we'll talk more about solutions. So we left off looking at the vapor pressure, calculating the vapor pressure of mixtures. So I showed this graph, which is essentially just showing graphically Raoult's law. So Raoult's law says that to calculate the vapor pressure of a mixture, so if you have 2 components, A and B, you have to consider the vapor pressure contribution of each of those components, so component A and B. But the problem is that these partial pressures is proportional to the mole fraction. How present are each of those components? So we see mole fraction of A and B is applied to get those partial pressures of each component. So we looked at 2 examples, one where the solute and water, the solute was non-volatile, so like a solid, like dissolving salt in water or sugar in water. In that case, the solute is non-volatile, so essentially one of these terms just goes to 0. So like the solute term, the partial pressure contributing from sugar or salt is just 0. So we just consider the partial pressure, vapor pressure coming from water. I like to think of these equations the same, whether you're calculating it for a sugar water solution or an ethanol water solution. So we use the full equation if both components are volatile. Both of them exert a partial pressure on their own, where we use the mole fractions of each, multiply them, add them up to get the total pressure. So this graph is showing, okay, what if we have 2 volatile liquids? If you think, oh, if we have pure A, and I wrote in these numbers to match the numbers we did in the previous example to kind of show it in a different way than just a pure calculation. If we have pure A, and I tell you A exerts a vapor pressure of 126, if we have pure A, if we fall along this mole fraction line and it's pure A, this liquid is obviously going to exert 126 because it's pure A. If we have pure B, that liquid is going to exert 285. But once we start mixing them, based upon the ratio of the mole fraction, we'll fall at a vapor pressure somewhere between these 2 points. And so, you know, if we measure an actual vapor pressure somewhere lower, closer to 126, then we can be confident that more A is present in that liquid phase. And so this straight line describes exactly Raoult's law, exactly, following this equation and mole fraction. But, you know, in lab, we don't oftentimes, there's theory and then there's observation, what actually happens. And so when inspecting Raoult's law, we're assuming particles are not interacting at all. but in fact, particles are attracted to one another. And so the idea here is when the attractions between your solute and your solvent are very strong, you will actually measure a slightly lower vapor pressure than what Raoult's law predicts. And that's in lab. But for the most part, we are sticking right with these calculations within Raoult's law within that straight line. But just know if attractions are really strong, it'll deviate downward a little bit. Okay, so that's mixing two liquids, two volatile liquids. So we're going to move on to other properties of liquid, or of liquids, of mixtures. Mainly we'll be talking about water. So we know when we mix stuff in water, what happens to the vapor pressure of water when you put mixed stuff in it? Like, let's say salt. It lowers, yes. So our trends are, from the beginning part of this section, it's vapor pressure lowering. Happens when you add more salt or add more sugar. We get freezing point depression as we add more stuff, as we add more solute. You get boiling point elevation. And then the last one we'll talk about today is osmotic pressure. So we're going to talk about freezing point depression and boiling point elevation. So we just talked about Raoult's law and said that, when you add stuff to water, in the mixture, vapor pressure is lowered. When does a liquid boil? When does water boil? When it's 100 degrees Celsius, yeah? Always? Always? No, not always. So when does a liquid actually boil? When its vapor pressure equals external pressure. So at 100 degrees Celsius, what is the vapor pressure of water on Earth? 1 atm, yeah, and that's why water boils. But here's the thing, that's pure water. What did we say about salty water? It has a vapor pressure that's lower than in the pure form. So when we're working with mixtures that have already lowered vapor pressures, we're starting at a lower point, okay? And so it's gonna be harder to get water to achieve a vapor pressure of 1 atmosphere to start boiling. And so that's why we have boiling point elevation. Because our vapor pressures are lowered in the mixture, we elevate those boiling points. Same idea for freezing point depression is once you have a salty water or sugary water solution, we have to get that solution colder in order for it to freeze. And so how we navigate and do calculations for these two properties is these equations, which are basically the same, where I can say, the freezing point depression, so the extent water freezes in a mixture, is equal to this term, I times K, which is a constant, times little m. What is that? Little m. Molality, yeah, so not molarity, it's not a mistake, it's little m, it's molality. So all of these properties, the extent of freezing point depression or the extent of boiling point elevation depends on the concentration of your mixture in molality. That's the key here, all right? We'll talk about I in a second. K, freezing point constant, and the boiling point constant, they're given here in a chart. They're typically given to you, but these are constants specific to the solvent that you're trying to boil or freeze, again, usually water. All right, okay, so let's talk about this. Okay, let's try this equation out. All right, so this freezing point depression, it's how much we deviate from the normal freezing point of water. So let's just remind ourselves, what is the regular freezing point of water? 0 degrees Celsius. So whatever we calculate here, we're going to have to subtract from 0 degrees. Again, freezing points are always depressed when we add junk, when we make mixtures, when we add salt or we add sugar. Okay. So let's navigate this equation. So I didn't tell you what I is. This is a new term. This is called the Van't Hoff factor, where the Van't Hoff factor accounts for the electrolyte behavior of your solute. All right? So I'm going to build off something you already know, and that's, do you remember net ionic equations? How to build those? Yeah? When did we split a substance for a net ionic equation? What did it have to be? Strong electrolyte and soluble, meaning aqueous. Had to be both those things. And then we split it. So remember how we split stuff if you had NaCl aqueous, what did that split up into in a net ionic equation? Sodium plus, chloride minus. So that's what I'm showing here, right? So when you put salt in water, you put one thing in. How many things do you get out? 2. So the Van 't Hoff factor for sodium chloride is 2, yes. But what about sugar? What kind of electrolyte behavior does sugar have? It's a non-electrolyte. Yeah, there are no ions. So when you put 1 unit of sugar into water, how many units do you get out? Just 1, because it's a non-electrolyte, no ions form, all right? So here, NaCl, you put 1 in, it's a strong electrolyte, you get 2 ions out, a cation and an anion. Just for completeness, tell me, what about calcium chloride? What do you think the Van 't Hoff factor for calcium chloride is? 3, yeah, have confidence, yes. When you put calcium chloride in water, you get a calcium 2+, and you get 2 chloride minuses. So that's a Van 't Hoff factor of 3. So just relate it to like net ionic equations and how you split up those electrolytes. Okay, so that is I. So based upon the identity of your thing, you can usually infer what I will be. In this question, I give you molality for all of them. And I give you the freezing point depression constant, all right, which is 1.86 degrees Celsius per molal, meaning for every 1 molarity of this solution, it's going to depress your freezing point by 1.9 degrees Celsius. Okay, so at this point, it is just plug and chug. So delta TF for this solution is negative. Don't get confused about the negative. The negative is just trying to remind you that this is freezing point depression. Whatever number we calculate needs to be subtracted to make the freezing point of water lower than it is in the pure phase. So negative 1 times the constant, so 1.86 degrees Celsius per molal, times the molality given, so 0.1, who cares about sig figs, molal, right? And so you calculate this, and you get that the freezing point depression is negative 0.186 degrees Celsius. So this solution, this sugary solution, is going to have a freezing point 0.186 degrees lower than the normal freezing point. All right, so we're just subtracting it from 0. From 0, so that means the actual measured freezing point of this solution is going to be negative 0.186 degrees Celsius. All right. If we were working with a different freezing point temperature, we would subtract from that. All right. Like if your liquid already freezes at 20 degrees Celsius, you'll subtract from 20 degrees Celsius. Right. But in this case, because it's we're working with water and it's 0, I know these numbers are the same. Okay. So there is sucrose. What about NaCl? How do you think our answer is going to differ? What's the only variable that's different? It's just 2. So we're going to get a doubling of the freezing power, okay, or the freezing point lowering power for sodium chloride. So let's just do the work for completeness. So negative this time Van 't Hoff factor of 2, 1.86 degrees Celsius per molal, same concentration, 0.1 molality, so we get a doubling effect. We get even more lowering power here for our salt solution because it is there's more ions present. Salt gives us twice as many particles in that solution. And so that means our freezing point for salts is going to be negative 0.372 degrees Celsius. Okay, so for completeness, tell me, describe me what the freezing point depression, what the freezing point temperature of 0.1 molality calcium chloride will look like. Will its freezing point be the same as any of these? No. How's it going to be different? It's going to be 3 times that of which one? The sugar one. Yes, because the only difference is the Van 't Hoff factor is 3 for this example. Yes. So it looks like what really affects our freezing point depression are these 2 terms, I and the concentration. Here I kept the concentration the same, so we could really just look at I, our Van't Hoff factor, to see the freezing point depression ability of these solutes. Okay, so let's put it all together. So I have 5 different solutions here. One's pure water, and I want you to rank them from the highest to lowest freezing point. So we're going to still look at the freezing point depression equation. But note here, how are these different, I don't really want you to calculate all of them. So let's just do it a quick way where we can recognize these different solutions have different I values, different Van't Hoff factors. Do the different solutions listed here, do they have different molalities? Yeah, okay, so we need to account for that. But do they have different K constants? Will they have different constants? No, they're all going to be the same because it's all water. So we can just ignore that K value. And so our strategy here to rank these is let's inspect the I times M product for all of them, and that will give us our ranking. Because K is the same for all of them, so that doesn't really matter. What's really going to differentiate the extent of the freezing point depression is the I times M product, the number, the concentration of solute particles actually present. So let's just go ahead and do that and quickly look at the identities of these things and determine what is the Van't Hoff factor for them. Okay, NaCl, how many particles do we get? 2. Sugar, 1. Pure water, so this is going to have a molality of 0, okay, because it's not a mixture. So we can just go ahead and say the I times M for pure water is 0, right? There's no freezing point depression for water because it is pure water. All right, back to sugar is 1, and then magnesium chloride is 3, yes. Right, so we got I. Now we just need to take that I value, multiply it by the molality given to now compare the products of those two. All right, so I'm just multiplying I, that we just did, times the molality, and I'm going to put the product on the other side. So we got 0.4 molality of particles present in that first solution, 0.1 molality of sugar solution. The other sugar solution, also a Van't Hoff factor of 1, but it's more concentrated, it's 0.3. And then magnesium chloride is 0.6 molality. All right, so just based upon these concentrations, these are the concentrations of particles in these solutions. So remember, these colligative properties, they depend on the concentration of solute particles present. So which solution is going to have the lowest freezing point, the most freezing point depression? The magnesium chloride, because it has the highest concentration of salt present. So we're going to see that magnesium chloride is the lowest freezing point, okay? The most depressed. Okay, it's going to be the most depressed because it's the highest concentration, versus the sugar is going to be the least depressed because it has the lowest concentration, while pure water is going to have the highest freezing point, because does pure water have a freezing point depression? No, it's 0, all right? And then everything else is going to be lower than that. So the highest freezing point is going to just be the pure water. And now we're just ranking on I times M, all right? So next lowest, lower than pure water, is going to be the 0.1 sugar. Then it's going to be the 0.3 sugar. Then it's going to be the 0.2 sodium chloride. And then it's going to be the 0.2 magnesium chloride, all right? These need molalities, okay? It's, again, not just concentration of your solute, because it's weird. It's like, oh, it's 0.2, 0.2, 0.3, then 0.1. But again, we have to account for the Van't Hoff factor. You get a tripling of particles from magnesium chloride. You put 1 of those in, you get 3 out, versus sugar, you only put 1 in, you only get 1 out, all right? And so you got to account for that I times M there. So just taking the I times M product will help you get the relative ordering of freezing point depression. More concentrated solutions have more depressed freezing points. Okay, so that is the Van 't Hoff factor, freezing point depression. Oh, what if I change this question to which one has the highest boiling point? How would it change? Would we have to do more calculations? No. Which solution is going to have the highest boiling point? Water? So what is the property? It's freezing point depression, boiling point elevation. So higher concentration, higher boiling point. So now, which one has the highest boiling point? Magnesium, and then the lowest will be pure water. And then it's going to scale the exact same. Okay, all right. Okay, so, you know, I literally just taught you the Van 't Hoff factor 3 minutes ago. And so those values that we looked at, like 2, 3, whatever, those are the ideal values. Because here's the thing. What we do on paper, not always the same as what we observe in lab. And since you guys are in 1220, we're doing more advanced stuff, we're going to talk about deviations from the Van 't Hoff factor. Because it doesn't always happen that NaCl has a Van 't Hoff factor of 2. Sometimes it's not that way, right? Oh yeah, so let's just like remind ourselves. NaCl, when you dissolve it in water, you get a Na plus and a chloride minus. So its Van 't Hoff factor is 2. Okay? So, okay, you put NaCl in water, you get 2 particles out. You get a cation and an anion. In the simplest terms, can cations and anions in solution interact with one another? A cation is what charge? Positive, and an anion is negative. So what naturally happens? They're attracted to one another, yeah. Okay? So this whole idea of Van 't Hoff factors, we're making an assumption that the ions stay apart forever indefinitely. But here's the thing, cations and anions are attracted to one another. So for a split second in time, the ions can pair up with one another, lowering the Van 't Hoff factor for a split second. But then they might separate again and still be free ions. And so that idea of ion pairing, that the ions can pair up in solution, even though it's still a strong electrolyte, they just might slightly pair up with one another, is what lowers the Van 't Hoff factor away from ideal. When we're talking about deviations of the Van 't Hoff factor, it's always going to be a lowering from ideal. Like NaCl has a Van 't Hoff factor of 2, the ideal version. But what we measure in lab will always be a number slightly less than 2. Never will you measure a Van 't Hoff factor greater than 2 for NaCl. All right, it's always a lowering when we're talking about deviations. Okay, so ion pairing, this is the phenomenon that happens that creates these deviations. Here's a good picture, right? Like here, you got chloride and sodium. Those are 2 separate particles, but in a moment of time, these 2 can pair up with one another, essentially lowering the number of particles that are totally in that solution. This only happens for like a fraction of a second, then it goes away. Okay, so let's look at some examples. All right. All right, here's a table of examples, but I want to tell you what are the criteria for ion pairing, therefore deviations to the Van 't Hoff factor. So the first one is concentration. So just remember, more ion pairing, more Van 't Hoff factor deviation. Okay? More ion pairing. So think about it. How often will ions pair when the concentration is high versus the concentration is low? Where will ion pairing be more abundant? When the particles are close together or far apart? Close together. So concentration makes ion pairing more abundant. So therefore, you will get more deviations in the Van 't Hoff factor. So we can see that in this table. Look at sodium chloride, right? There's the Van 't Hoff factor for sodium chloride at 0.1 molarity, and there's the Van 't Hoff factor at 0.001 molarity. So this is dilute, and then the first one was concentrated. All right. We know sodium chloride has an ideal Van 't Hoff factor of 2. So the deviation is greater when it's very concentrated. All right, so concentration affects your deviations, increases ion pairing, lowers your actual observed Van 't Hoff factor. All right, ion charge also affects Van 't Hoff factor, because the idea of ion pairing is just that you have a cation and anion that are attracted to one another momentarily, reducing your number of particles. So think about it. Ions, are they more attracted when it's plus one minus one, or plus two minus two? Where's there more attraction? Plus two minus two. Yeah, so if you have high charges, okay, so high charges, plus one, minus one versus plus two, minus two, this one's gonna have more ion pairing, the plus two, minus two, more ion pairing. Right, when it's plus two, minus two. Let's see, let's look at the example. Let's look at sodium chloride, and magnesium sulfate. What is the Van 't Hoff factor for magnesium sulfate? If you put that in water, what ions do you get? You get a magnesium. What else do you get? Sulfate. Do you get sulfurs and oxygens all broken apart? No, sulfate stays together. So what is the Van 't Hoff factor? 2, yes. So look, in an ideal world, sodium chloride and magnesium sulfate have the same Van 't Hoff factor in a perfect world. But if we apply the idea of ion pairing, they both are lowered, but which one's lowered more? Magnesium sulfate, due to what factor? Its charges. Yes, magnesium sulfate is a plus two minus two ion, plus two minus two, versus NaCl just plus one minus one. So we see a larger lowering, more deviations for magnesium sulfate. Concentrations are the same, okay? So it's this ion charge that's affecting that, right? And then finally, the last one is ion size. Typically, when ions are small, you have a high charge density, and so you'll see more deviations when your ions are small. So for example, if I had lithium fluoride and sodium chloride aqueous, right? Let's pretend they're both the same concentration. What are their Van 't Hoff factors normally? 2 for both of them, but which one deviates more? It's going to be lithium fluoride because it's smaller. All right, deviates more, meaning it's going to be a lower value than 2, right? It's going to deviate further away from that ideal value of 2. Okay, so, we didn't finish this. Let's just get the, what is the ideal Van 't Hoff factor for potassium sulfate? 3, yes, because you get 2 potassiums and a sulfate out. Yep. And so again, you see at dilute concentrations, you still see a deviation, a lowering of that Van 't Hoff factor, but at higher concentrations, ion pairing is more abundant. All right, so that's ion pairing. Let's put it all together. We already did this. We already did, the I times M ordering of these 5 substances. We did not need to consider ion pairing for this original question because the I times M product was the same for all of them. It was the same. So we can just do I times M, rank them, be on our way. So let's do this follow-up question where we do have to consider ion pairing. Let's look at sugar, 0.4 molarity sugar, and ask ourselves, where does that belong? Where does it belong? So let's just get its I times M off the bat. What's its Van 't Hoff factor? 1. And then what's its molality? 0.4. So its I times M is 0.4. Oh crap, I forgot one thing. Can I go back a slide? All right, we talked about Van 't Hoff deviations. Wait, why does the Van 't Hoff factor deviate? For what phenomena? Ion pairing. So what's the one row I didn't explain yet? Sugar, I didn't explain sugar. So based upon these observations in this table, does sugar deviate from its Van 't Hoff factor at all? No, it doesn't. But think about it. Deviations from the Van 't Hoff factor are explained by ion pairing. Does it make sense why sugar does not deviate from its Van 't Hoff factor? It has no ions. Yes, so if you have a non-electrolyte solution, all right, where it's Van 't Hoff factor of 1, it is not going to deviate from the Van 't Hoff factor because there are no ions, okay, for ion pairing to occur. All right, and so that's a big deal because we needed that to answer the next question. So I forgot to mention that. Sucrose, no ion pairing possible. No ion pairing possible. All right, but that's just for non-electrolytes like sugar, glucose, organic things. But any ionic things that are electrolytes can ion pair and deviate. Okay, so let's go back to this question and ask ourselves, where will 0.4 sugar belong? So we just got its I times M product, it's 0.4. Do you see the problem? Yeah, what's the problem? It matches something else, right? It matches something else. It looks like it should have the same freezing point depression as my sodium chloride example. Both of them are 0.4, you know? And so if this is an exam, there might not be an option that says, oh, the sodium chloride, it's the same as that one. We might not have that option. You have to order it lowest to highest. So let's apply our idea of ion pairing to this question. So with the idea of ion pairing and deviations from the Van 't Hoff factor, is magnesium chloride's I times M product exactly 0.6? No. Is it going to be slightly higher or lower? Lower, yes. Is that the lower sign? Yeah? Okay. What about NaCl? Is it actually going to be 0.4? Nope, it's going to be slightly lower than 0.4. Perfect. Okay. What about sugar? Is it going to be exactly 0.3? Yes, it will be exactly 0.3. I was trying to trick you, but you were good. Why is it exactly 0.3? It cannot ion pair. It can't ion pair, so there are no deviations there. And then the 0.1 sugar will also be exactly 0.1. And so now we can answer the question, in what spot, A, B, or C, will sugar belong? That 0.4 sugar go. In spot A, yes, it's going in spot A because 0.4 is a larger number, more freezing point depression than a number slightly less than 0.4. All right, it's going in exactly 0.4. Ion pairing and deviations from the Van 't Hoff factor are especially important when you get yourself in a situation where you have two solutions with the exact same I times M product. At that point, if both of your I times M's match, you want to resort to ion pairing to actually finish up the question, right? Because you might try to say like, oh no, they have the same freezing point, but that's not true if ion pairing is involved. Okay, how do we feel about that? Do you feel smart? It's like I teach you something and I'm like, wait, tricked ya. It's harder than that. Okay, so that is freezing point depression. So let's talk about the last consequence of colligative properties dissolving stuff in water, and that's osmosis, or osmotic pressure. Osmosis is a product of that. So osmotic pressure, this is a weird property to describe. It's hard for me to describe, but let me just tell you the trends, okay? Liquids, when in systems with semi-permeable membranes, such as our bodies, okay? I like to jokingly call myself a big saltwater bag because that's what I am. I'm filled with water, I'm filled with salt, okay? I'm a salty solution. And so our bodies are filled with these semi-permeable membranes, our cells. And they contain salt. It's not just pure water, it's salt. And so the trend is those salty solutions exert a osmotic pressure depending on the concentration of the salt. So the trend is for osmotic pressure. This is the symbol for osmotic pressure, it's pi. As your concentration of salt increases, osmotic pressure increases. Also as temperature increases, osmotic pressure increases. We can see that from the equation for osmotic pressure, which if you squint your eyes, this is actually just PIV-NERT. It's just PIV-NERT rearranged, because osmotic pressure is a pressure unit. But we also include I, the Van 't Hoff factor. So if we just rearrange PIV-NERT, we get that osmotic pressure, pi, is equal to our Van 't Hoff factor times N over V, which is molarity, moles per volume of solution. So this is molarity, all right? We are using molarity now, not molality anymore. R, this is the same R from the gas law, so 0.08206 liter ATM mole Kelvin, and then temperature in Kelvin. So really, again, if you squint your eyes, this is just PIV-NERT. But we're calculating osmotic pressure of a solution that has a concentration of salt or whatever. Okay, so what is osmotic pressure? All right, I will tell you now that I gave you the definitions, that higher concentration of salt or solute, higher osmotic pressure. So if I have a system where I have two different solutions with different concentrations and they're separated by a semi-permeable membrane, what that means is that water is free to move on either side of the system, okay? Water can move, but the solute cannot move, only water can move. So what I have right here on one side is pure water, okay? And then on the other side, I have a salty solution because they're solute dissolved. So just based upon the trends, which side has the higher osmotic pressure? The pure water or the salty side? Salty side, okay. So what does osmotic pressure mean? Osmotic pressure is the pressure required to push down on this arm, on this liquid, to keep water from traveling to dilute the other side. Because right now, this picture, this is not concentrated, lots of water. This side, very concentrated. So osmosis naturally happens where water will tend to dilute the other side, so both sides have the same concentration until they have the same osmotic pressure, all right? And so what osmotic pressure is, so naturally, if we just let that system hang out and we let it do its thing, what we would see is water would leave this side and enter the other side, diluting it. All right, and then you'll see what would happen. It would look like this. And so again, what osmotic pressure is what amount of pressure is required to force the water molecules back so both arms are equal. That is what osmotic pressure is, right? But I think what's good enough for us is if you know higher concentration of salts, then higher osmotic pressure that thing exerts, all right? Okay, so that's what that is. And again, the big idea here is that water can flow through these things, through the semi-permeable membrane, but the solute particles cannot. And so only water can move over to try to dilute that system to make the concentrations or the osmotic pressures equal. Okay, so let's actually do a question, I think. Yes. Because if you just look at this equation, you know, we can't just give you numbers and have you calculate it, plug and chug. No, that's 1210 stuff. So let's actually calculate a quantity that's more useful to us, right? Because basically what this is PIV-NERT. So let's use osmotic pressure to calculate the molar mass of something, all right? So molar mass has a unit, grams per mole. And whenever I'm confused or lost, I look to the units, okay? I just look to the units and I ask myself, what's the unit? And look at those units and see how can I mess with what information is given to get those units. So we're calculating molar mass. Let's get grams per mole. So I am telling you, you have 2.6 grams of an organic compound, a non-electrolyte. We dissolve it in water. It has this final volume. The resulting solution has this osmotic pressure at this temperature. Cool. That sounds like pi. And then 25 degrees Celsius, that's 298 Kelvin. That sounds like temperature. Cool. So we have a lot of parts here. Calculate the molar mass. So again, let the units guide you. If we want the molar mass of this compound, I need the gram amount of the compound present, and I need the mole amount of this compound present. And as long as I get those two things, I can calculate molar mass. Do I have one already? Do I have one already from the information given? Yes, which one? The top one. Fantastic. I just like to take inventory because it makes me happy. I see, oh, I have the numerator already. I'm halfway done. I like to think that. So I just need to figure out how many moles of stuff, how many moles of compound I have, and then I'm home free. So obviously, we're going to use the rest of the information given in this problem to figure out how many moles of compound I have. So let's go back to this problem. Fill out this blank. If I tell you that this is an organic compound, it's a non-electrolyte, what does that imply about its Van 't Hoff factor? It must be 1. Is it going to deviate at all? Nope, it won't. So we're just going to stick with 1. Perfect. So if we look at our osmotic pressure equation, we can see what we have and what we don't have and what we can calculate. So we are given pi, osmotic pressure. We just figured out what I is. R is a constant, we have temperature. So you can see we have everything we need to calculate molarity. So let's just do that. Let's just plug everything in, get molarity. So molarity of this solution. Okay, so molarity equals pi over I times R times over T. So pi was given as 0.566 atm. I we just got as 1. R is the gas law constant, so it's the same one. Note how I'm using liter, atm, mole Kelvin. Osmotic pressure is given in atmospheres, but if I gave it to you in torr, just like Pivner, you got to manipulate it a little bit before using this gas law constant. And temperature is always in Kelvin, so 298. All right, and so you get that the molarity of this solution with this particular osmotic pressure is 0.0214 molarity. I think there's a 6 in there somewhere. All right, so is that my denominator? Nope, it's not. That's molarity. We want moles. So again, remind yourself what molarity means. What does molarity mean? Moles per liter. So this means that this solution has 0.02146 moles of compound dissolved in 1 liter of solution. That's what it means. Okay? Oh, so is it 0.02146 moles? No, that would be how many moles are in 1 liter. Do we have 1 liter of solution? Nope, we have 0.25. So we got to utilize now that last piece of information, the volume, where, okay, I know the concentration, so let's start with the amount that I actually have, which is 0.250 liters of solution, right? Because I have less moles than this molarity value, all right? This is how much moles of stuff are in 1 liter of solution, but I only have 0.25. So 1 liter of solution contains 0.02146 moles, and so we see that this 250 milliliters of stuff has 0.005786 moles of compound present. So I used the given osmotic pressure to calculate molarity, the concentration, and then further went on to use the volume given to get its mole amount. Okay, so is that squared number, do I put that in the denominator? Is that the number I put in the denominator? Yes, it is. So let's go ahead and finish this question. So grams of compound given already, 2.610 grams of compound over the mole amount we just calculated, 0.0058786 moles. And so you get, there's your gram per mole value. It's somewhere around 450 grams per mole, right? And so we were able to get that by knowing the mass of your solute and measuring its osmotic pressure, All right, so that is kind of a more advanced way we can utilize the osmotic pressure equation rather than just giving you numbers and you plug and chug, because that's really no different than gases, what we did in chapter 10 in Chem 1210. Okay, So last bit about osmotic pressure. It's very important in living things because, like I said, we are just big salt water bags, okay? And so our cells have a certain concentration of salt, and if the plasma and the liquid inside of our body has a different concentration of salt or solute, we're going to have a different osmotic pressure difference on the inside and the outside of the cell. If that happens, that's really bad. Okay? When you go to the hospital and they hook you up to an IV, what is in that IV bag? Salt. What would happen if they put just plain old water in there? You'd probably die. Okay? This is why, because of the osmotic pressure differences, all right? When the osmotic pressure on the inside and the outside of the cell is the same, okay, there's no tendency for water to travel through the semi-permeable membrane of your cell to inflate or shrink up that cell. Water will move freely in and out as it pleases. It reaches this nice equilibrium. When everything's the same concentration, you have the same osmotic pressure on the inside, the outside of the cell. We call this an isotonic solution, where the solution has the same osmotic pressure as our blood, and that is what's in a IV bag, is solutions that's salty enough to have the exact same osmotic pressure as the fluids in our body, all right? Because we do, obviously, does it not sound fun to have your cells blow up or shrink? Yeah, that's not a good thing. So you want things to remain isotonic. That's when osmotic pressure is equal. But once we have unequal osmotic pressure, yeah, bad things happen. So a hypotonic solution means you have a very dilute solution your red blood cell, or your cell is sitting in, all right? That you have, low concentration on the outside of your cell. So what happens is outside is low concentration, inside of the cell's high concentration of salt. So water will penetrate your cell to try to dilute all that salt. And what happens is that your red blood cell blows up with water, all right? Blows up with water and it explodes. And that's bad. And so what do we call that? We call that hemolysis, I guess. I'm attempting at teaching biology right now, but trying to utilize as much chemistry as possible, right? That's a hypotonic solution. Versus a hypertonic solution is when the concentration of salt on the outside is too high, right? Concentration on the outside way too high, not enough water, okay? So that means there's a high osmotic pressure on the outside of your cell. So what's going to happen is the water inside the cell is going to try to dilute the outside. So your cell's going to shrivel up because it's going to lose all that water, right? So this is why you don't drink salt water. You don't draw, maybe not salt water, don't drink seawater. I think that's what I wanted to say. All right, like if you're stuck in the ocean, they say never drink this seawater, because if you only drink salty water, this is what's going to happen to your red blood cells. Your fluids in your body are going to become too salty, increase that osmotic pressure. All of your red blood cells will shrivel up and undergo crenation here, and that does not sound too pleasant. Right? Don't drink seawater. On the other hand, you might have heard of stories of like marathon runners or like triathlon athletes. They, do these big endurance tests, and they drink a butt ton of water. But they drink so much water, and they don't replenish the salts in their body, that some athletes get very, very sick from just water, because that's due to hypotonic solution. You're drinking so much water that it changes, dilutes these salts in your body so much that hemolysis might start to occur. And that's how athletes who they say OD on water, this is what's happening, essentially, all right? Because, if you think about being an athlete, I don't think about that much, but I imagine if you're on a big endurance test, you can drink water, but what else do they give you? Gatorade. Yeah, what's Gatorade? It contains salts. It contains electrolytes, all right? It exerts a high osmotic pressure. So when you drink Gatorades or things with electrolytes, you're maintaining an isotonic solution in your in your body, all right? So drinking a normal amount of water every day is fine. It's counteracted with the salts that naturally occur in our food, the foods that we eat. But it's when you're doing really strenuous activity, sweating a lot, drinking a lot of water, it is important to replenish your electrolytes through a sports drink or something like that so you feel better. Oftentimes, if I have a headache, I know it's because I'm not drinking enough water, okay, because I'm like over 30 now and it sucks, my body's like deteriorating. And so I can sense when my osmotic pressure is off. So I used to, like take an Advil or something if I had a headache, but now it's mostly because I'm not drinking enough water, but now I've actually started adding like liquid IV to my water a little bit to replenish my electrolytes. And it does help. If I have a headache and I drink like half a liquid IV, it usually goes away. Yes, so there you go. And so what you're doing is utilizing the whole idea of keeping the salt concentration, osmotic pressure inside and outside of your cells equal. Because when it's unequal, bad stuff happens. Okay, great. All right, so last part of the chapter, colloids, a special type of mixture. All right. So in Chem 1210, we talked about two types of mixtures. What kind? Homo and hetero, yes. We basically ignored heterogeneous mixtures because they're harder to study, but the big difference between those two, hetero and homogeneous. Heterogeneous mixtures, they have different phases, particles settle over time, all right? So we can call those types of mixtures suspensions. We're still gonna just mainly ignore those, all right? Where you have like solid particles mixed in with your liquid. A saturated solution would be an example of a heterogeneous mixture because you have solid present and the solution around it. If you shake it up, the solid doesn't dissolve, it just kind of floats around, but then over time it settles to the bottom, right? In 1210, we also talked about homogeneous solutions. These are true solutions, okay? Homogeneous mixture is a synonym for solution, whether it's the gas, liquid, or solid phase. But for the most part, we're talking about liquids here. So for example, NaCl. Aqueous is a true solution because it's uniform. Salt water looks the exact same as pure water. Those particles are dispersed evenly throughout the entire sample. And we're going to look at some other properties here too. So one of those is the Tyndall effect and the scattering of light of these different mixtures, okay? So if we took a flashlight and shined it on a solution, so such as sodium chloride, if we shined a flashlight on salt water, that light would travel just straight through the solution and not scatter light at all because the only particles in this solution are water, sodium cations, and chloride anions. Those are too small for light to scatter. But if we go on the flip side, if we look at a suspension, a heterogeneous mixture, where there is solid particles floating around, if you shine light on it, those solid particles will scatter the light, and you'll see it. You'll see the little solids like floating down to the bottom, okay? So that really distinguishes a solution and a suspension, that light will not scatter a solution at all, because the particles, a true solution, the particles are too small. All right, that's what we learned in 1210. But now, because we are better, we're going to kind of look at an intermediate type of mixture, and that's a colloid. A colloid is weird. Colloids seem like true solutions. They're uniform. An example is milk. Milk is a colloid. Okay? But on the particle level, if we zoomed in really, really finely, we would actually see that there are particles of different sizes, and they're inconsistent. So that would make it a heterogeneous mixture. But the thing is to our eyes, they look like true solutions. Because milk seems like it's uniform, but it's not. Milk is the first sip you drink the same as the last sip you drink? Yeah, it is. Yes, yeah. I would hope that the milk that if you were drinking a cup of milk and you drink a sip of it, and then the last one in the cup, it's going to taste the same, right? So it has uniform properties, okay? So doesn't it seem like it's a true solution? Yes, because it has uniform properties. You know, like the nutrients, they're scattered throughout it uniformly, all of that. But if we look at a microscope and look at milk, what we'll actually see, the microscopic view of milk, we see these fat globules that are in inconsistent sizes. Okay, so these inconsistent particle sizes, they're small enough not to settle over time, but they're large enough that they are inconsistent. So that's what a colloid is, that we have these inconsistent particle sizes, but they're small enough to stay in solution, right? When we buy milk, what are like there's two words that kind of describe milk. One is pasteurized, meaning that they heat it up enough to kill bacteria. What's the other word? Homogenized, meaning they mix the crap out of it to make the fat particles really, really small so they don't settle over time. Okay. I don't know if you've ever tried to make butter. I have, yes, of course I have. All right, and all you do is you take cream, which is just very fatty milk, you shake the heck out of it to try to get all those fat globs to fall out of solution. So you can separate the liquid part from the solid part, right? That's how you make butter. You can literally take a mason jar, fill it with cold, heavy cream, not that much, shake the crap out of it for a really long time. Be good if you like put something in it to try to agitate it, and you too can make your own butter. If you want to try it. Okay. All right. You don't need a special contraption to do it. Okay. All right. So, cool thing about colloids, right? So if you put milk in front of a flashlight, you will see this, that a colloid, because its particles are big enough, okay, to be inconsistent, but small enough to not settle out of solution, is what you'll see is if you shine light on it, you will see the beam of light scatter particles, okay? You won't see the individual particles, but you will see like the beam of light going through. Here's another example of the Tyndall effect. Here's a laser beam shining through a solution. So let's just say this is like NaCl, this is salt water. All right, and then this is a colloid. See how you can actually see the laser beam because it's scattering on the very, very small particles that are in there, but the particles are small enough not to settle and be a suspension and settle over time. All right, and that's the Tyndall effect. That's what differentiates a true solution from a colloid. On the outside, they might both look the same. All right, so let's do the last slide here. And then this is an example of a how you can make a colloid mixture with stuff that's readily available, soap, okay? And so we're bringing back the ideas of intermolecular forces, like dissolves like, whatever, and soap, because soap is special. Because if we think about like washing our hands, if we have like oil on our hands, will water alone clean that? No, you got to put what on your hands? Soap, yes. So the purpose of soap is that they're amphiphatic, meaning that there's both a hydrophobic end and a hydrophilic end. Hydrophobic means water-fearing, but to us, if applying intermolecular forces, it means that you have a nonpolar end of your molecule. The nonpolar end associates with the fats, the oils, okay? The polar end, or the hydrophilic, water-loving, they oftentimes say polar, okay? But if we look at what that polar end looks like, it's actually also ionic, all right? So fats will interact with the nonpolar parts via London dispersion forces. That's the matching strongest IMF there with oils. But water, okay, oil, okay? But water, what IMF is important going on here, you think? Hydrogen bonding and another one. Well, dispersion's there, but it's not super important. What's the other strong? It's ion dipole. How do I know it's ion dipole? It's ionic. Yeah, look, it's charged. So not only is hydrogen bonding happening, but also ion dipole is happening, both which are the strongest IMFs out there. And that's why water associates to the polar or the ionic end. And dipole is happening too, but that one's weaker, right? So you can see, oh yeah, oil's gonna associate over here, water is gonna associate over there. So that's how you clean your clothes and your body, is that the like snaky nonpolar end associates with the oil. On the outside, you have the polar ionic parts that are interacting with water. And so it can carry the oil droplet away via those soap molecules because it's both associated with nonpolar and polar things. Yeah. Okay, so, the question is, how do we know there's hydrogen bonding? So these oxygens actually have lone pairs on them that I didn't mention, or they're not drawn there, but they're there, okay? And so water can hydrogen bond. So water has a very electropositive hydrogen on it, okay? And so if we look at this part of the molecule, do we see anything that looks like it's attracted to this hydrogen? Yeah, any of these lone pairs on oxygen. These oxygens are very electronegative. They can associate also. They can hydrogen bond, form a very strong hydrogen bond with a water molecule. A soap cannot hydrogen bond to itself, but it can hydrogen bond to a water molecule. Does that make sense? Okay, all right, perfect. All right, so it is both polar and ionic. Okay, so how do colloids come into this? So at a certain concentration, if you have a lot of soap molecules, all right, here's just kind of a cartoon version of this where you have the polar end of soap and then the non-polar end over here. At a certain concentration, all of the non-polar tails tend to aggregate with one another, leaving the polar heads on the outside. And so if you dissolve a little bit of soap in water, you get these tiny little micelles that form that are basically just these kind of soap molecule structures. That they're like these spherical things where it's non-polar tails on the inside, polar heads on the outside. And so these soap micelles are very effective at cleaning and capturing non-polar things like oils. All right, so this micelle can have any number of soap particles in it. And so when you have a solution filled with micelles, each of the micelles are a different size, but they don't settle out of solution. So that is an example of a colloid because we have inconsistent sizes of micelles. So if the word micelle kind of sounds familiar to you, does anyone use this at night? Yeah. So we call this micellar water. Yes, it also contains micelles. It is a colloid. So really what you're buying is soapy water. That's it. But I tested, and I forgot to bring my laser pointer, but I mentioned that a mixture of a bunch of micelles is a colloid. So if you take your micellar water at home and you take a laser pointer and you shine it through your micellar water, you will see scattering of light. Versus if you do the same thing for a pure water, if you take like a water bottle of pure water or salt water and you shine light, you won't see anything. But if you take your micellar water, you will see particles scattered. So that's something you can do. Usually I bring the demo, but I forgot, I'm sorry. All right, so yeah, so that's makeup stuff. All right, any questions? Nope, so that's the end of chapter 13. So that means, what about homework? It's due on Monday. Perfect. Okay, so we're going to move on to chapter 14. So I can blow stuff up. Okay, so in this chapter 14, so could you grab the slides? This is the start of our journey of K. We're going to start with small k, baby K, little k. This is rate constant. And then we're going to talk about big K next chapter, and for many chapters, this is equilibrium constant. So little k, small k. So make sure when you say K, you're referring to what K. But for now, we're just doing small k. All right? So this chapter actually has 2 homework sets, and we're splitting it up by midterm. So midterm 1 material ends at slide like 47 or 48. It's in the slides, you can see it. And so I also have the homework set split up that way as well. All right. Okay, so we just got to get through 48 slides up until activation energy and the Arrhenius equation. Then the rest of that material will be on midterm 2. But we're still going to forge ahead. All right, we're going to finish chapter 14 before the midterm. But just so you know that reaction mechanisms and catalysis won't be on there. All right. So chemical kinetics. We've never talked about how fast or slow reactions go. When we think about chemical reactions like A plus B equals C, some like combination reaction, usually up until now we've really only done BCA tables, limiting reactants, those types of things. It's like, oh, you combine like 5 A's, 10 B's, you know, all that. Right? So now we're looking at more details of chemical reactions, and that's how fast they go. So let's kind of just put it into perspective. We all know this reaction, right? I mix hydrogen and oxygen. You tell me, is that a fast reaction or a slow reaction? Fast. I think it's pretty fast, yeah. But what about another reaction like rusting on a car? That's fairly slow. Why? Why is this fast and the car rusting is slow? Okay, think about it. All right, so let me, now that these are the factors that affect reaction rate. They all depend on collisions, and this is something we've ignored up until now. Reactions will only happen when your two reactants collide with one another with enough energy. Both of those things have to happen. They need to collide with one another with enough energy. So if you just gently graze two atoms together, it may not make a reaction, okay? But if you bash them together, a reaction might happen, okay? So with the idea of collisions, we can kind of use our intuition and think, okay, more collisions, faster reaction. So what do we think about how does concentration affect how fast a reaction goes? Think about collisions. Will a reaction happen faster at high concentration or low? High, yeah, because if they're high, right, all of your reactants are really close to one another and you can just grab them and bash them together. Versus if the concentration's low, they're spread out different parts of your container. They're on different sides of the stadium. It's going to take a long time for those two particles to collide with one another. All right, next, temperature. Which one has a faster reaction, high or low? High, yeah, why? They're moving faster. Yeah, they're just, moving faster at higher temperature, more average kinetic energy. All right, physical state of your reaction, solid, liquid, or gas, what do we think? Gases, why? They're just moving around more. Solids, they're just like hanging out, not doing anything. So it's very unlikely or happen very slowly that two solids will come together and react with one another, because solids are basically stationary. Okay, presence of a catalyst. So think about how we use catalyst in our everyday language. Like, for example, the idea of the electron catalyzed my passion for chemistry. I love electrons. So what do we think? Will a catalyst speed up a reaction or slow it down? Speed it up. Okay, perfect. All right, so let's test it. What kind of reaction is going to be faster? A reaction between two solids or two gases? Two gases. And so if we go back to the idea of hydrogen balloon versus, what was the other example I gave? Rusting of a car. A car is what physical state? Is a solid. So although rusting of a car, the oxidation is with oxygen. So we have a solid interacting with oxygen, but the solid is stationary. Okay, so that reaction is going to happen a lot slower. So let's just check our intuition and make sure that reactions between gases happen quickly. So this balloon actually has oxygen in it. And so it's going to be this one's a lot louder. It scared me last class. So this one's the big one. And so we need to practice safe ear protection. Oh, I need the goggles. Okay. All right, ears, everyone, this one's very loud, very, very loud. I promise you're going to regret it. Yes? Okay. Everyone, ears, 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 ears. Okay. Okay, you tell me, is this reaction fast or slow? Yeah. Yeah, when we add oxygen, it's fast, it's louder. Yeah. I warned you. Doesn't get old. It doesn't get old. Okay, so you tell me, fast or slow? Very fast. Yes, it was very fast. Very fast. But the idea is this reaction doesn't happen unless I initiate it. right? So what I did was not a catalyst, but it shows the idea of there's this activation energy. There's a little push I have to give the reaction before it falls downhill to be highly exothermic. Okay, all right, so good, yes, that reaction's fast. So let's look at these pictures. Which one is the fastest, assuming they're all at the same temperature? Number 2, but for what reasons? They're all gases, but also the concentration is higher in those ones. All right, so for 2 reasons. Because this one, 3 is a gas, but the concentration's lower, less collisions. Collisions lead to reactions. Okay. All right, so got 10 minutes, perfect. So let's talk about reaction rates. And differentiate it to how we've been talking about reactions previously. We've been looking at stoichiometry in previous years. We can say, oh yeah, look at the coefficients. One of this combines with one of this to give us one of this, or something like that. That's what this reaction is saying. I'm combining one of that and one of this to give one of that and one of that. We could have done a BCA table, okay, before, change, after, inspect that. But now we are looking at, okay, how do the concentrations change over time, right? What's the rate of consumption of a reactant? At the same time, what is the rate of production of a product? So the great thing is that it still follows stoichiometry when talking about rates at a specific time or rate, an average rate, all right? So if we look here, the stoichiometry between this reactant and this product is 1:1. So if we compare the rates, what we can say is that the rate of consumption of the reactant is equal to the same rate of production of the product. All right? It's a 1:1 ratio. If I eat 5 of these per minute, I should also produce 5 of these per minute. All right? Don't let this negative sign freak you out. That negative sign implies that this is a reactant and it's being consumed, right? Versus on the other side, it's a product, so it's being produced, so it's a positive sign on this side. All right. So for any generic reaction, the rates, they're all of consumption and production. They're all related to one another via stoichiometry, but the coefficients end up in the denominator. So for example, if we were combining 2 A's and 3 B's with one another, when we compare the rates, those coefficients become the denominators in these fractions. All right. And again, the negative signs imply consumption. Positive on the side implies that we're producing something with this reaction. Okay, so let's just quickly look at this graph and notice some interesting things. Okay, so this graph is showing this reaction. One of each of these things is combining to make HCl and that other thing. So we're starting with something and its concentration is going down. So what do you think this substance is? Is it a reactant or a product? It's a reactant, yeah, because it's being consumed. And so here I'm just tracking concentration with time. So if I actually wanted to calculate a rate at any certain time, it's not the actual y value of this graph. Rate is actually the slope at any certain point, or the tangent. The tangent at any time, that is our rate. Does our rate stay the same throughout the course of the experiment? No, it doesn't. So we will inspect that as well. So if this sounds like calculus, it is. But we're not actually going to do any calculus, just so you know. Okay. So those are some ideas we'll come back to. So let's work through these and look at, differentiate stoichiometry from rates, because it is different. But we still use the coefficients the same. So here's the reaction we all know and love from reaction stoichiometry. The reaction 2 breads plus a cheese gives us a sandwich. So let's just use our intuition a little bit. If the rate of consumption of bread is negative 10 breads per minute, what is the average production of sandwiches at the same time? 5. Yes. I feel like we're like, yeah, 5. We have to consume twice as much bread to make one sandwich. So if we eat up 10 breads, we can only make 5 sandwiches over that same time period. So 5 sandwiches per minute. And this is a positive 5 because we're producing it. But for completeness, let's also do cheese. What's my rate of cheese also in this same time interval? It'll also be 5, yeah, because again, 2 breads for every 1 cheese. So 5 cheeses for every 1 minute or whatever, okay? But what's the sign on this cheese? It's going to be negative because the negative implies it's being consumed. All right, that's how we relate them all. See how it's all related by stoichiometry? 10, 5, 5. So this is how the generic equation comes into play and how we can relate them all. So how we would write the rate expression to compare all of these is we take the the coefficients and turn them into the denominator number, where reactants get a negative sign. So for bread, it's going to be -1/2, the 2 goes on the bottom, times the change in bread over time. Okay? So the 10 that we just got, that number goes into this parenthesis. That's where it goes. And we can set that equal to the rate of change of cheese. So negative, because it's a reactant, 1/1, change in concentration of cheese over time. And then the last one for bread, now we can finally use the positive sign, but it's just positive 1/1 times change in concentration of sandwiches over time. Right? And so these 3 numbers we calculated, 10, 5, and 5. That's what goes in these parentheses. We need those fractions there to make them all equivalent. So I'll show you what I mean. Right? So I was given that the rate for bread was -10. I'm just going to drop the unit because I want you to see how the numbers work out. Equals the rate of change for cheese, which we just got, which we said was -5, equals positive 1/1, the rate of change of sandwiches, which was 5. Are all of these things equivalent to one another? Yes, they are. So that's how that equation works. We can use the stoichiometry to make a relationship between the rates, but the rate expression relates all of them together, right? We do need the negative signs there. Coefficients becomes the number in the numerator. Okay, so let's just do one more. All right, but for an actual reaction. Okay, but again, just think cheese, bread, sandwiches. So if I tell you the rate of consumption of HI is 0.24 molarity per second, that should be a negative there. I forgot the negative because this is a reactant. What is the rate of appearance of H2 at the same time? So note the stoichiometry. So what do you think? If it's 0.24 for HI, it's going to be what for H2 gas? 0.12 molarity per second for H2. Perfect. All right, because it's a 1-to-2 ratio. Okay, now what if the rate of appearance of H2 is 36 torr per second? What is the rate of disappearance for HI over the same time period? So you might be thinking, that's not a concentration. For gases, pressure is proportional to concentration. All right, so just treat the numbers the exact same. And I have the proof over here, just rearrange Pivnert. Pressure is proportional to concentration, right? So the relationship here, 1 unit of hydrogen for every 2 units of HI, what do we think that rate of consumption for HI will be? It's not going to be 36, but it's going to be twice that. It's going to be 72, yes. Then I have to consume twice as much HI at any one point to get that rate of appearance of H2 in the same time interval. All right, so let's write the full relationship with everything again. And again, this is just how we relate all of the values in the same line to make them equivalent. Reactants get negative signs, and coefficients go in the denominator. So 1/2 change in concentration of HI over time. So that could be a molarity per second, torr per second, whatever, equals positive 1 over 1 change in concentration of H2 over time, whatever number that is equal to also positive 1 change in I2 over time. So what that means is whatever hydrogen gas's rate is, I2 will also have the same production rate as well. Okay, so we'll stop there. Remember, chapter 13 homework is due on Monday. It's like a 2-hour set. Due date doesn't mean due date. Have a great weekend. I still have office hours.